演講。那好，那接下來這位講者是遠從日本而來，他是 LY Corporation 的 iOS Engineer Yuki Aki。Yuki 目前在 LINE 負責改善 Build System。他經常在各大會議分享 Swift 的開發心得。同時也是多個開源專案的貢獻者，包含Swift Compiler、Fastlane， 還有 Xcode Gen。那今天的演講他會以英文進行，那就讓我們歡迎 Yuki Aki。
チョコミントよりも X コード。I'm surprising. What happened? Okay, so yeah, 你好 so 我是Ju. Because my mother is Chinese, so I a little knows Chinese self-introduction, but only it. Okay, so yes, hello everyone, and this is Yuki from LY Corporation. Yes, in this talk I'll address the Swift performance, its evolution, and how we as a Swift developer can approach it. Yeah, that is not my introduction because I want to introduce Swift, not me. Yeah, great. So it's today's agenda. First, I'll explain the Swift merge platform support and runtime behind it, which are focusing on the performance. Next, I'll touch on the challenges of Array, explain the fundamentals of Swift performance through how Array works, and show how inline Array can help address those challenges as an example. So next, finally, based on all that, I explained what's important for us to be mindful of and to understand about Swift evolution. Okay, so first, let's talk about the Swift merge platform support, its runtime, and the performance aspects that come with them. Oh, I found it. So Swift has been growing into a language with potential across the many platforms. Of course, there is a mainstream language on Apple platforms like iOS, watchOS, visionOS, macOS, and tvOS. It's also available on the other operating systems like Windows and Linux, and even supports web development paradigms like the WAS. And experimentally, it's also moving towards supporting embedded systems, which are minimum and have structured environments. Furthermore, an Android work group has been launched in the Swift community, and adoption for Android development is also progressing. As you can see, the Swift supports a wide range of platforms and continues to evolve. When it comes to understanding its multi-platform nature and its performance, what we really need to look at is how Swift works under the platform. A Swift program doesn't run on its own. It needs an environment that makes it behave as like Swift. In other words, it's a runtime. This runtime is called libSwift core on most platforms. So what exactly does libSwift core do? As I mentioned earlier, libSwift is a Swift runtime. In other words, it's a foundation that enables Swift to run on a platform. libSwift core mainly exists to support Swift dynamic features. In construct, the compiler handles the static side, like the checking your code correctness, performing optimization, and building. Therefore, the dynamic refers to the things like reflecting memory layers, performing allocations, and managing memory through the automatic reference counting. The way Libby switch core is distributed varies by the platform. On upper platform, it's bundled with the OS. This is why some features of newer switch version aren't available until you update to the latest OS. The benefit of having the OS provided is that each application doesn't need to include the runtime and prevents upsides from growing. For Linux programs, you can choose to link the runtime statically or include it as dynamic library. Unlike upper platform, without considering the OS version, you can use the latest switch features right away. On Windows, the current approach is to bundle it with the app as a dynamic library. So on the OS environments we've talked about, the runtime set up the switch execution environment for us. However, the runtime is by no means small, and in environment like embedded systems, where memory and storage are limited, including it is not practical. So Switch allows you to build the programs for embedded system, includes a much smaller Switch environment. This is called embedded Switch. Embedded Switch is an executables for tailored for embedded environments. By dropping some dynamic features to reduce binary size, it delivers smaller Swift programs suited for embedded system. So how does the embedded Swift stay small? As you know, Swift offers a wide range of features, and some of them are especially tied to runtime. For example, features like untyped throw, reproduction, any and weak require runtime metadata and type information. In embedded systems, because environment is limited, this feature leads to runtime overhead and increase your program size. Embedded Swift provides a subset of Swift language by removing such features that would cause overhead in embedded systems. Embedded Swift supports the standard library. Features like codable, encodable, and decodable aren't supported because they require the reflection on runtime. But most other familiar features are supported. However, there are challenges, and one example is array. Switch array is implemented as dynamic heap allocated container to provide rich functionality. While it's safer use than the C-style array, those rich features come with overhead. Oh, I noticed that we have many array talk today. In embedded systems, using Swift array can be costly choice because that relies heavily on the heap. So how can we overcome arrays costs on embedded system? Starting with Swift 6.2, inline array offers one way to address this challenge. Let's look at what makes array costly and how inline arrays solve it. Also, we can see valuable hints about what Swift performance really means from array challenges and how it's solved by inline array. So let's dive in the take closer look together. Now let's look at challenges of array and walk through how inline array works. This is a kind of array code you all write all at time. Let's see how an array is stored in memory when this code is run. First, since the array itself is a struct, it's stored in the area called stack. You may already know about stack, but let's take a moment to review what the stack is. The stack is a memory-efficient region used for storing local variables and function calls. Data gets allocated and freed in a strict last in, first out order. I'll explain later, unlike the heap, it doesn't need memory management with reference count. To give you a clear image, let's look at what the stack actually is, and with example of real function code. First, let's see how the stack changes when we call this test1 function. When test1 function is called, the stack gets a new block data for it, holding the test1 function information like its local variable. Then, after running some code inside test1, as you can see, it's called test2. At this point, what happened to the stack? Well, just like before, the information for test2 gets pushed on the stack. Okay. Oh, sorry. I didn't know that my voice is small. Okay, sorry. Just like before, the information for test2 gets pushed on stack. In this way, each function data is managed on its stack frame. When test2 finished and execution returned to test1, so what happened to stack? Since the stack works in the last in, first out manner, it popped out from top frame test2 and frees the block. By releasing entire frame at once, all of the test2 data is cleared from memory. And when test1 finishes, it's popped and freed in the same way. It's clearly releasing all data from the function called so far. When you set breakpoints in Xcode, your app crashes. You've probably seen this screen. This list on the left is called stack. It's called call stack, which is the same stack I'm talking about. Each thread has its own stack, and you can inspect detailed information for each one right in Xcode. I also follows a similar flow, and it's stored in stack. But internal implementation uses a heap, so things are not quite that straightforward. To allow flexible addition and removals, an array maintains an internal buffer. This buffer is stored in the separate area from the stack frame. That buffer is stored in the heap area. Let's talk about heap. It's a flexible memory area used for long-lived or shared data like class instances. You can allocate and free memory in any order, but that means system has to keep track and manage it. Also, allocating from the heap is slower than using stack. I'll describe later about it. Let's also check how the heap works using a simple example. Here, as you can see, we look at code that works with an instance of some class type. First, the reference address to the class instance is stored in the stack. Then, the class instance itself is stored in the heap, and the address on the stack will point that heap location. When you call text or drop a reference to the instance, some count updates its internal retain count. This mechanism called auto-reference counting. That counter decides whether the heap object should stay alive or freed when it reaches 0. When it reaches 0, switch frees the object memory on the heap. That's how switch manages memory in the heap. Auto-reference counting actually comes with hidden cost. Like behind your switch codes, the compiler inserts the extra instruction to update the reference count. This runs every time a reference changes and over time. That hidden work adds up to the performance costs. Another thing to watch out for with heap memory is fragmentation. For example, let's imagine we store some instance in the heap. As the switch codes run, objects get freed and allocated, leaving small gaps scattered throughout the heap. This state and where small gaps are left scattered around is called fragmentation. Now let's try creating larger class instance and putting into the heap. As you can see, the heap has free space here and there, but there isn't spot large enough for this large class instance. The allocator may have to scan from the beginning to find a big enough block near to the end for a long time, or fail to find. In short, heap usage can incur the overhead from fragmentation and the search for contiguous space. So putting data on heap can introduce various kind of overhead. And in limited resource environment like embedded system, that impact becomes especially noticeable. Let's also touch on the overhead involved when working with regular array data. For example, when you add an element to array, there's still a potential for overhead. Because array is expected to be modified, its buffer is usually allocated with some extra capacity beyond the current number of elements. But when that extra capacity runs out, it allocates new larger buffer. Then all existing elements plus the new one are copied into a new buffer and referenced from the array struct. The old buffer is then freed. From performance perspective, it's worth knowing that this kind of copying and reallocation can introduce overhead. So here's the pitfall of array. Even if it's just a small fixed array, Swift still puts it on a heap. In environments with limited resources, like embedded systems, that become a cost. And if array grows, you've got a buffer reallocation and copying. So the question is, how do we work on this? Here, let's take a look at a good example of old C array. A C array is basically a fixed length array stored on the stack. Since embedded Swift can call into C, so you could call C language code that works a lot of elements. But because it has no bound checks and causes unexpected behavior, so ideally, we still want to write it in Swift. And that's a point of motivation behind introducing inline array to Swift. Inline array will be a stored stack, so we don't need to care overhead heap for fixed size array. Inline array, in a way, combining Swift safety with C array performance. It's stored to stack with no heap allocation. It's bound checks yet still highly performant. Inline array also has benefits in iOS development. Even on iOS, the stack advantages are significant. It keeps data on the stack for low latency access, and it eliminates heap allocation overhead in performance critical code. Finally, let's take what we learned today and think about what's important for understanding Swift evolution. Swift is now designed with multi-platform use in mind, and we discussed earlier, it also has growing focusing on performance consensus features. To keep up with the Swift evolution and truly understand, I believe these three things are key. First, understand the motivation behind the evolution. For example, code like the inline array we looked earlier might not seem beneficial at first glance. But every new feature comes with underlying motivation or specific problems it aims to solve. Without understanding this, it's hard to see their value or know when to use them. By actively digging into proposals for new Swift features, you can uncover these motivations and turn them into your tools in your own power. Next, understand Swift performance. Swift offers many high-level conveniences, but these sometimes hide cost under the hood. So like heap allocation, reference counting, or buffer reallocation, knowing where these codes come from and know how they differ across platform helps you write codes that's both expressive and efficient. Finally, understand the mechanism of your code. Please look at your everyday code through the lens of performance, asking, is this the right tool? Am I using it correctly? And could it be improved? It's built a deeper understanding of Swift. Finally, I'd like to share a few conversations that can help deepen your understanding of Swift. These talks and materials are great resources for keeping up with Swift evolution and strengthen your knowledge. I encourage you to check them out. Thank you for listening. So I hope this make your Swift journey great. 謝謝。